I'm very pleased to have this opportunity to talk with you tonight about my second favorite planet, Venus. Let me see if I can share. Let's talk about Venus. And of course, the context for this is that we live in an age of comparative planetology, this sort of iconic family portrait over here. These are images that we're sort of getting used to, but it's remarkable that with the exploration missions of the last 60 years now, we have these photographs of all these planets in our solar system, and of course all the other data, and we can start to really do comparative planetology and see the planets in relation to one another and start to develop general principles of planetology, of how planets evolve and what they're like out there. And of course, of interest to astrobiology, and really I think of interest to everyone, is the question of what conditions elsewhere might facilitate some of the very interesting developments that we've enjoyed here on Earth, life and all that it means. And of course, we also now live in the age of exoplanets, and this is one of the real revolutionary developments of our time. When I was in grad school in the 1980s, I know back in the dark ages, we learned that there ought to be exoplanets because everything we understood about the origin of the planets suggested they were just a byproduct of ordinary star formation around our ordinary star. But we didn't have the ability to detect them. They were something we believed in, but didn't really have data for. We inferred their existence. And of course, now all that has changed, and we know that almost all stars have planets. And we're just starting to learn not just that they exist, but learn something about them. And tools like the James Webb, of course, are that's how we're going to do it. But in the meantime, there are only a few planets we can actually get to with spacecraft. And so those are very precious to us as the sort of local truth that allows us to establish the context to understand the planets of the universe. And among these, I have a particular fondness for this trio of worlds, Venus, Earth, and Mars, because these are the three planets that are really Earth-like in the sense that they're terrestrial planets, rocky planets that have significant atmospheres. And out of all the planets we now know about in the universe, and we are learning that in fact there are a lot of rocky planets with atmospheres, but these are the only ones that we can actually get to and examine up close. So this trio, this comparison of these three worlds has been a particular fascination of mine. And out of that, the planet Venus and its comparisons to Earth is something that I've really been fascinated with for a long time, really my whole career. Venus is so like the Earth in some ways and so unlike the Earth in other ways. We don't get many chances in this field to do controlled experiments in our idea for our ideas about planetary evolution. It's not like chemistry where I could say I have this hypothesis and I'm going to take this one beaker and do something identical but change one variable in this beaker and do a controlled experiment. We can't do that with planets, but the Venus Earth comparison is almost the closest we'll ever come to a controlled experiment, because it's two planets that we think started off very similar, the same size as far as we can tell, same initial composition more or less, and yet they've evolved in very different directions due largely to their different distances from the sun. So it's something of a controlled experiment in planetary evolution, at least as maybe as close as we're likely to come. And of course, Venus has long been a fascination for humans, way before we had spacecraft and anything like what we would consider science. People were very aware of Venus because it's the brightest object in the sky other than the sun and the moon, and it moves in these mysterious ways, just appearing for a few months in the evening and then disappearing and appearing again for a few months in the morning. There's sort of a flirtatious behavior where it's never up in the middle of the night, but it just kind of peeks around at dawn or dusk, and often in some kind of interesting dance with a crescent moon. It's lovely and just interesting. And so people have long been aware of it. And again, way before science, Venus was the subject of story and mythology and worship and all that. There are many great Venus stories and origin stories and so forth. The Mesoamericans in particular, all over the Americas, the indigenous peoples were avid observers of Venus, and amazingly good at tracking and predicting its motions, and imparted all kinds of interesting stories and meaning to that. And of course, Venus was a big player in the Copernican Revolution. Once we entered into the age of telescopes and the scientific revolution, Venus, the observations of Venus by Galileo were key to the revelations of the Copernican Revolution, as sort of depicted here in this cartoon by my friend Carter Emmart. Galileo's here observing Venus and noticing that it goes through phases, and its apparent size grows and shrinks as it goes through those phases. And the only reasonable way to explain that is that both Venus and Earth were orbiting the sun. And so this was a major piece of evidence in the mind-blowing realization that the Earth was not the center of the universe, and that everything in the solar system orbited the sun. So that was an important role that Venus played in helping us understand where we really are. And after the Copernican Revolution, once we realized that Venus was a planet, for a long time, it was believed to be a very Earth-like place. And this was reinforced by some early observations and inferences that you could tell that Venus had a thick atmosphere if you closely watched what happened when Venus transited in front of the sun. And you could tell that Venus was covered in bright clouds just by its great reflectivity. And some clever early observers inferred that it was roughly the same size as Earth. So everything we knew about Venus before the space age, almost everything we knew, suggested that it was very similar to Earth in size and in having an atmosphere and clouds. And so people logically inferred that it probably was very Earth-like. And the image of Venus was of a sort of tropical planet, a kind of a swamp world. The idea being, well, it's like Earth, but it's a little closer to the sun, and it's full of clouds, so it's probably dripping wet and maybe full of tree ferns and so forth. So this is just a picture I took on Kauai once, but it to me it reminds me of the sort of pre-space age view of Venus that was very popular, not just amongst science fiction writers and so forth, but scientists in the scientific community. The idea of Venus as an Earth-like, maybe sort of a warm, wet Earth was very popular. And this led to a lot of fun science fiction. When I was a kid, I was very fond of Isaac Asimov's Lucky Star series, and one of them was Lucky Star in the Oceans of Venus, where Lucky, our hero, battles giant jellyfish and telepathic frogs in the oceans of Venus. That also led to a lot of kind of goofy pop culture. This is Zsa Zsa Gabor playing the chief Venusian scientist in the movie Queen of Outer Space. And, so there's a lot of great pre-space age lore and stories of Venus. All that changed in 1962 with the launch of this spacecraft, Mariner 2, which was the first successful spacecraft to any planet. It had a twin spacecraft, Mariner 1, which would have been the first, but Mariner 1 went off course during launch. The rocket did, and the range safety officer was obligated to hit the button to blow the rocket up because it was veering dangerously off course. So that's what happened to Mariner 1. But Mariner 2, a few weeks later, was successfully launched and made it to Venus, not without some problems and difficulties and drama, but it made it there, and it was the first successful planetary mission. And Mariner 2 actually really carried just one instrument to observe Venus, and you can see on this image here this sort of protruding object, which is an instrument called the microwave radiometer. And the idea was to scan across the disk of Venus, measuring the intensity of the microwave radiation, to try to understand that prior to this mission, some anomalous radiation had been observed coming off of Venus. And it was maybe, some scientists believe that was incompatible with Venus being a tropical Earth-like place, that it meant that Venus had to be very, very hot on the surface. But other scientists thought, no, that microwave radiation can't be coming from a hot surface. It's some atmospheric phenomenon. So this instrument was specifically designed to test that by scanning across the disk of Venus and measuring how the microwave radiation changed across the disk. And it's kind of a classic experiment. If the radiation is coming from the surface, then the intensity of the radiation should peak in the middle of the disk of Venus. That should be where most of it's coming from when you scan across it. That's called limb darkening. It's darker on the edges. And if the radiation is coming from the atmosphere, then it should be highest on the two edges and dip down in the middle. That's called limb brightening. And so Mariner 2 made it to Venus, scanned across the disk, and indeed what it saw was a clear indication of limb darkening. In other words, this radiation was not coming from the upper atmosphere, it was coming from the surface. And that proved that Venus is very, very hot on the surface. And so this was the first ever successful experiment at another planet. And what's interesting to me when I think back on it is it's very unusual that you have an experimental test on a spacecraft that can simply decide between two fundamentally different ideas about a planet. Venus either is very hot on the surface or it's not. Here's this one observation, you're going to have the answer. Usually our results are much more incremental than that. It's not like you do the experiment and it's like, oh, it's this planet, it's not that planet. But this was the first ever experiment ever done on another planet. And I think it's, in a way, it's almost the best or almost only example of a major hypothesis being proven or disproven with one simple observation. So I don't know. I just think that's kind of interesting to reflect on. Anyways, so with that observation, the idea of Venus being a sort of Earth-like place vanished immediately. And it began to sink in. It took a while to really sink in, but it began to sink in just what an alien, extremely un-Earth-like place Venus is. And the realization has sort of hurt. It was seen as a big disappointment. And in fact, here's the editorial from the New York Times the day after this result was reported. It's entitled, "Venus Says No." 1962, New York Times, right after this result came in. And I won't read the whole thing, but it starts, "The first message from the Venus probe to site for shortly after historic flyby on December 14th, blah, 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 helps to answer one all-important question, whether or not life in some form existed on Venus and hence elsewhere in our solar system and possibly also beyond it." And if you jump to the end here, I highlighted it. The message from Venus well, let's look at this paragraph. Mars now remains our only hope of turning this universal dream into reality, and the evidence so far is not very encouraging. The message from Venus may mark the beginning of the end of mankind's grand romantic dreams. Ooh, that hurts. So what a bummer Venus is, but in a way, as I wrote in my book, which is called Venus Revealed, that was kind of unfair to Venus because we put it up on this pedestal and had all these unrealistic expectations. And then when it didn't meet those expectations, we were very disappointed. But it turns out, fast forward years later, that Venus is a very, very interesting place, really fascinating and really priceless for our basic knowledge of planetary evolution in ways that we didn't anticipate then. So after it sunk in how hot Venus is, and we started to send a few more missions there. I won't go through every mission, but the United States and the Soviet Union were in this space race in the 1960s, and Venus was a relatively easy place to get to in terms of energetics with the rocket. It's actually the easiest other planet to get to in terms of delta V, how much rocket fuel you need to get to. It turns out to be a difficult place to explore because of its nature, but it's an easy place to get to if you just want to lob a rocket somewhere beyond Earth. And so with some of those early missions, American and Soviet missions, we began to understand some of the sort of bulk facts about Venus. And we started to put together this comparative picture of the two planets, Venus and Earth. And what's fascinating, if you look at just this list of a few basic properties of Venus and Earth, is how these top three numbers, these top three columns show how similar Venus is to Earth. In terms of diameter, this is in kilometers, but they're almost the same. Venus is a little bit smaller than Earth, but we don't know of any other pair of planets that are so nearly similar in size to one another. And in terms of mass, again, Earth is slightly larger, but not much. And then you can translate that to escape velocity, and Earth's is just a little bit higher than Venus's, and that turns out to be very important for things like atmospheric evolution, where the ability of a planet to hang on to its air, its atmosphere, is determined by the escape velocity, how much energy it takes to leave that planet gravitationally. But then if you look at these bottom three columns in this graph, you see how unearthly Venus turned out to be when we started to explore it and send probes into its atmosphere and so forth. The pressure on Venus, the surface pressure, is almost 100 times. It's 92 times the surface pressure on Earth. So you would reach that pressure on Earth if you go down in the ocean about half a mile. It's really extreme. And again, the temperature here in Celsius on Venus is just, the average temperature is really, really hot. For those of you who prefer Fahrenheit, it's almost 900 degrees everywhere on Venus all the time on the surface, except for the highest mountains. It gets a little cooler, but day, night, it's the same. Pole to equator, it's the same. It's really, really hot, ridiculously hot. Excuse me. And then this bottom graph, I mean, I could throw a lot more numbers at you, but these are just some of the striking similarities and differences. This is the amount of water on the two planets. And what's striking here is that Earth has 100,000 times as much water as Venus. Venus is really, really dry. And for two planets that are so similar in density and seem to be made out of similar stuff in terms of the rocks that they were originally formed from, that's really kind of bizarre. What happened to Venus to dry it out to that extent? We'll get to that. But the exploration of Venus turned out to be very, very difficult to learn a lot more about Venus in terms of what its surface is like and so forth. And that's because not only is the atmosphere so extreme on the surface, but the whole planet is covered in clouds, completely enshrouded. And these clouds are fairly featureless if you look at them with your own eyes in the visible. But here, this image is in the ultraviolet, and it's got these dark, sort of still mysterious dark markings. We're still trying to figure out what that dark stuff is that absorbs in the ultraviolet. We have some ideas about it. We could talk about that, but at any rate, the clouds themselves turn out to be made out of concentrated sulfuric acid, battery acid. So that's why Venus is so hard to explore. You can't see the surface from orbit or from a telescope, at least not in the visible. And to get to the surface, you have to go through corrosive clouds, and then you have to get through an atmosphere that is 900 Fahrenheit and incredibly high pressure. So it's not an easy, it's an easy place to get to in terms of rockets, but it's a really hard place to explore once you get there. So in order to figure out what Venus was like beneath those clouds, we required a lot of ingenuity and perseverance. And I realize now I'm borrowing words from Mars' expression, perseverance, ingenuity, but these are also words of just human effort. And the Soviet Union turned out to be really, really good at exploring the surface of Venus. They really, their biggest success, I would say, in space exploration was that they are still the only nation to have successfully landed spacecraft to operate on the surface of Venus and take photographs and measurements there at the surface. Not an easy thing to do given those extreme pressures, but this, in a museum in Moscow, you can see what these spacecraft look like. They're basically just these giant insulated diving bells surrounded by phase change materials, which keep it cool just long enough so that it can land on the surface, take some pictures, take some measurements. And these things lasted for about an hour on the surface before they fried. And due to those Soviet efforts, we actually got photographs of a handful of places on the surface of Venus. These are all, this is a sort of compilation of images from the Venera landers at the sort of half dozen sites where they managed to land these things. And you can see a sort of similarity. There are all these sort of flat platey rocks, which we now recognize as kind of ancient eroded volcanic rocks, and some fine material. And this is basically the extent of our actual photographic imagery of the surface of Venus, something that we plan on changing in the next decade. But we do have a lot of radar imagery, but in terms of close-up actual photographs, this is basically it. Oh, and in color, they look like this. Although the color, that sort of reddish orange color, is not actually the color of the rocks, which are rather gray. That's due to the fact that the light is being filtered through that incredibly thick atmosphere and through those clouds. And like the color of deep sunset colors on Earth, where the light is filtering through so much atmosphere, the blue shorter wavelength light gets filtered out, and what's left is this sort of murky red light. And that's what it would actually look like if you were standing on the surface of Venus. If you had a good enough suit so that you could stand there for more than a nanosecond without without having your proteins instantly denature in the heat. Anyways, so those Venera missions from the Russians were a great success. And in the late 70s, the United States sent a mission that was also very important in furthering our understanding, a mission called Pioneer Venus. And you see an artist's depiction here on the upper left. This was a spacecraft that had an orbiter and then also 4 entry probes, 1 large and 3 small probes. And you can see here at the bottom where those probes went. One of them was called the day probe, one was called the night probe. And then what's labeled here is the sounder probe, or we often call the large probe, was the one that had mass spectrometer and sort of more instruments to sample the air and so forth on the way down. But it did these simultaneous traces of temperature and pressure and wind speed and illumination and measuring the atmosphere composition on the way down. And that really helped to enrich our understanding of what that atmosphere was like. We still have a lot of questions, but a lot of what we know goes back to this Pioneer Venus mission. And it's remarkable to consider that this was 1978, and this is the last time that we sent an entry probe into the atmosphere of Venus. It's never been done with 21st century instruments. The Russians did send a balloon called Vega in the 1980s, which did some really cool measurements, but nothing that went down through the lower atmosphere since 1978. So this is something I'll get to later in the talk that we're now planning on doing with a modern probe with modern instruments. And boy, we got some questions for Venus now that we're hoping to answer soon with these newly approved upcoming missions. So after this sort of first wave of exploration in the 60s and 70s, we started to put together a picture of what Venus was like and how it became that way. How did Venus get to be so hot and so dry on the surface? And we don't fully know the answer, but we started to put together some ideas, which I would call sort of almost a cartoon understanding, at least a plausible explanation. And the sort of question, where did Venus go wrong? Maybe that's an Earth-centric way of phrasing it. I suppose if you were a Venusian, you could say, where did Earth go wrong? Except for we doubt there are any Venusians. And so if you favor a planet with the ability to create complex life like Earth, then that might be the normative value, which would allow you to say that it was, in fact, Venus that went bad. But regardless of that, you could ask, how did Venus end up so different? And it seems we have a plausible story that relates to the fact that Venus was born much closer to the sun. If you took two planets and they were identical to start off with, and you move one of them close to the sun, past a threshold of illumination. Now, remember, Venus is about 3/4 of the distance from the sun to the Earth. Okay, so if this is Earth, or this is the sun, and this is Earth, that's what we call 1 astronomical unit. Venus is 0.7 astronomical units. So it's, almost like 3/4 of the distance. So, but because of the inverse square law of solar illumination, that means Venus gets twice as much, almost exactly twice as much solar illumination as Earth. So it's a lot more sunlight. And we think that basically is the root of the root cause, because that can lead to what we understand, what we call the runaway greenhouse, which is a powerful positive feedback. And of course, I've got Jimi Hendrix here to represent feedback. But what I mean by that is when you heat up some water, as you know, you leave a pan of water out in the sun, it will start to evaporate. But water vapor itself is a greenhouse gas, is a very powerful greenhouse gas. As I say in my slightly nerdy slide here, it has greater infrared opacity, which means it absorbs infrared. So the more water vapor in the atmosphere, the more of a greenhouse effect there is, because the atmosphere is going to absorb more infrared. But that, of course, will lead to a higher surface temperature. And the higher surface temperature means more water will evaporate, and that will lead to more water vapor and more heating through the greenhouse effect. So that's a positive feedback. And basically, once it starts and gets beyond a certain point, there's sort of nothing to stop it. And in an extreme case, the oceans can boil off. And once they boil off, all that water vapor's in the atmosphere, and it's very vulnerable to ultraviolet light splitting the hydrogens from the oxygens, and the hydrogens fly off into space. And before you know it, you've lost your ocean. And we think that's the basic story of how Venus lost its ocean. And the result is, again, that Venus has 100,000 times less water than Earth. Now, that's a kind of a cartoon explanation, but did it really happen that way? And did Venus have an ocean originally? And crucially, for a lot of evolutionary questions, including the question of life, how long did Venus keep its oceans? Well, we don't know. We need more data, which we're seeking. But what about the surface of Venus? How do we know what it's like beneath the clouds? A big breakthrough came in 1989. We launched a spacecraft called Magellan. And here's Magellan being launched from the cargo bay of the space shuttle with its giant radio antenna at the top of the image here. And you can see its solar panels still folded up from the trip in the space shuttle. They're about to unfold there, and it's going to be sent on its way to Venus. And Magellan orbited Venus from 1990 to 1994 and basically revealed the whole surface of Venus to us. And the way it did that was with this big radio antenna at the top, which not only was the way the spacecraft communicated with Earth, but it was also its big scientific instrument. Because unlike visible light, which bounces right off the clouds, so you can't see the surface. Radar passes right through the clouds. So with Magellan, you could basically do, it's like flash photography, where you're bouncing light off of a surface, illuminating it, and then you're getting the return signal of that light and making an image. Well, you do that with radar. As Magellan orbited Venus, strip by strip, we call them ribbons, it would orbit, and underneath the path of its orbit, it would reveal one ribbon of Venus. And then as it, over 4 years, orbited around the whole planet, it filled in and imaged basically the entire, almost the entire planet at a resolution where you could see down to 100 meters or so. And here's Venus, mosaic of Venus in the Magellan imagery. And what you can see is that it's a very complex and varied planet, but much of it is dominated by kind of smooth plains, these relatively smooth areas, which turn out to be vast areas of flood basalts, smooth, vast flows of basaltic magma, sort of like the Columbia River basalts in the northwestern United States, or the Deccan traps in India, or the Siberian traps. You know, they're areas of Earth that are these vast plains of flood basalts, and much of Venus is like that. But then you can also see that it's broken up by these more reflective, which in radar reflective means rough, these rugged higher areas, which about 10% of the planet is very different from those smooth plains. It's high elevation, very rough mountainous terrain, some of which is volcanic, and some of these equatorial areas are dominated by giant shield volcanoes, sort of Hawaiian style shield volcanoes. Excuse me. And some of which are these areas that are known as Tessera. And here's a close-up of one of these Tessera areas. They're the most ancient and rugged areas on Venus. And these are we believe are the oldest areas, and probably areas that contain clues to the early history of Venus. So we're very interested in trying to eventually land on these tesseras and see what they're made out of. And in fact, the Da Vinci spacecraft, which I'm going to get to a little bit later on, we're going to descend and photograph one of these tessera areas for the first time with aerial descent photography, one of these rugged mountainous areas. So that's about 10% of the planet. Venus is made up of these ancient, very sort of tortured, rugged mountainous regions, and a lot of the rest of it is smooth plains. And then those smooth plains are peppered with volcanoes, an amazing variety and number of volcanoes with a lot of different shapes and sizes. These are what we call pancake domes. They're about 10 kilometers across, and they've made of some kind of very sort of sticky, not very runny magma. And then there are areas where there are just volcanic features that have, here's a place where magma has flooded through over this tectonic ridge. And then this is kind of another kind of volcanic feature where there's been you can see there's a fissure in the ground where these sort of petals of magma have flowed out. So Venus is just covered with all kinds of interesting volcanic forms. And we believe we have circumstantial evidence to suggest that Venus is still volcanically active. We have a number of lines of evidence that suggest this, although it's something we really want to test with new missions. So now that we have that kind of imagery, and also imagery of other planets in the solar system, we could do much more sophisticated job of comparative planetology, where we look at some of the same forms on the different planets, and they tell us stories of similarities and differences. In this case, for instance, you can see what look like river deltas from left to right on Venus, Earth, and Mars. And you can see a sort of similarity of form, where these are all places where some kind of liquid has flowed and then spilled out into a body, a flat or plane, or another body of liquid. So there's a similarity in form, and yet if you look at the details, they're all different, and they tell us of vast differences in these planets. In the case of Venus, this river delta You can even see a meander down here lower on. It really is very much like a river delta, but it's clearly not formed of liquid water because of the extreme environmental condition down there. We think it's formed by some kind of lava that at that temperature stays liquid for long periods of time and can flow for hundreds or even thousands of kilometers along the surface. Maybe some kind of a sulfur-rich magma. There's still some speculation on what that might be. In the case of Earth, you can see that this delta has been modified by life. And it's, that's the big force on Earth that doesn't exist on these other planets, that this is not just running water, but there are mangroves and biological systems that are interacting with the geology and the hydrology. And in the case of Mars over here, what you're seeing is an ancient eroded riverbed that's flowed into what once was a lake and now is a dried up crater. And you can tell it's ancient because there are even some craters superimposed on the landscape here. And craters are the sort of universal chronometers of the solar system. Even though we haven't been able to date rocks from other planets other than the moon yet, we can tell roughly how old the different surfaces are by how many craters they've collected. And speaking of craters, Magellan on Venus imaged quite a number of them. Turns out there are about 900 craters on Venus, and there's something kind of strange about the craters on Venus. This picture is typical, where there are fresh looking craters, but they're on a surface that looks like it's had the older craters erased by magma. It's as if at some point in Venus's history, there was massive volcanic flooding that erased the earlier history. And there's still some disagreements and different interpretations of what that history is, but it seems clear that there were times in Venus's past when there were massive outflowings of magma. Some people even call it a global resurfacing, where much of the earlier history of the planet was wiped out. And some of the craters on Venus just have this sort of very lovely form of these are called outflow craters, which you don't really see on other planets, probably caused by the fact that there was a lot of melting when this object hit the surface, just because when you're hitting a surface that's already that hot, then you can melt even more rock than you would in an ordinary cratering event. But as I said, there's something strange about the crater distribution on Venus. If you look at, here's a map of all the craters on Venus that were imaged by Magellan. And what's unusual is how uniform and random this looks. It's as if the entire surface is the same age. You don't see areas where there are a lot more craters and areas where there are many fewer craters, which would suggest older areas and younger areas. It's almost as if the whole surface was created at once. Of course, in the details, it can't have been that simple, but on a sort of a gross planetary level, it almost looks that way. Contrast that, for instance, with Mars. Here's all the craters on Mars, and you can see the southern highlands of Mars are clearly much older. They're ancient compared to the northern plains of Mars, which are clearly more recently resurfaced. And one of the ways we know that is by counting the craters on Mars. And there's this very asymmetric distribution where you can see there are much older areas and much younger areas, but Venus doesn't have that. It's as if the surface is to first order all the same age, which is just kind of strange and indicates that that Venus has a dramatic history that we're just really beginning to understand. And the surface is all relatively young geologically, by which I mean mostly younger than 1 billion years, as opposed to the surface of Mars, where if you picked up a random rock on Mars, it would be really unusual if it was less than 1 billion years old. It's much more likely to be many billions of years old, unless it's a windblown sediment, but the bedrock. Whereas on Venus, it seems as though most of the surface is much younger. So here's what I mean is, and this is something done by my colleague Jim Head, and this is just sort of a cartoon, but it shows a general idea of the age distribution of the different planets, from the left being really ancient, 4.5 billion years old, and to the right being present day. And if you look at the moon, Mercury, and Mars on this graph, then that shows that most of the rocks, most of the surface on those heavily cratered planets is ancient. And there's basically almost no surface that's younger than 2 billion years. Contrast that with Earth, where it's very hard to find a rock on Earth that's more than a few 100 million years old, let alone 1 billion years. You just can't really find any because Earth is reworking itself all the time. It's geologically alive. And if you look at Venus, we don't know the details. That's why there's question marks around this shape for Venus. But it's clear that that it's more in the category of Earth, of being basically recently, if not currently active. We're still trying to figure that one out, but it's basically a much younger planet with much more recent activity. And that was a big revelation that came from the Magellan mission. And that led to a lot of interesting questions of the atmosphere. And I won't get into a lot of detail on this, but this has actually been my major area of research, is how does the geologic history and the atmospheric history, how do those fit together? Because it turns out that Venus has a lot of complex interactions between the surface and the atmosphere and clouds. The active volcanoes on the surface feed the atmosphere with gases like sulfur dioxide, which react with water vapor and sunlight and make those sulfuric acid clouds. But those are also greenhouse gases, water and SO2, and the clouds affect the radiation. So all of that affects the surface condition, which then feeds back and controls the chemistry of how the surface is interacting with the atmosphere. So the climate of Venus turns out to be this very complex interaction of volcanism and radiation and chemistry, which is in itself controlled by the climate, which, you know, it's a large set of very complex feedback loops, which this is, I don't want to get too nerdy on you here, but this is the schematics for a Venus climate model that a colleague and I made and used to simulate the climate effect of a lot of these proposed geologic histories that came about in the light of Magellan. And what we found is that the whatever that volcanic history is, has probably also controlled the climate history and the nature of the clouds. And one strange, but I think true result we found is that the clouds today are probably the result of ongoing volcanism. In other words, if you stop the volcanoes at the surface and those sulfur gases stop entering the atmosphere, the clouds will probably go away in about 30 million years because the sulfur gases will get all eaten by surface minerals. So if we're right about that, then you can see with your own naked eyes evidence for active volcanism on Venus. Because when you look at Venus bright in the evening, as it's been until recently, and just now it's starting to come up in the morning. But when you see that bright disk hanging out at dusk or dawn, the reason it's so bright is because of that shroud of reflective clouds, which we believe are the result of ongoing volcanism. So you can, with your own naked eye, you go out early tomorrow morning, you can verify that there are active volcanoes on Venus, if our model's correct. You have to add that if, but that's why we need more data to understand if we're seeing this all correctly. So now let's talk about some more missions. And I'm going to rush here a little bit because I want to make sure that we get some time for discussion. But we had a mission called Venus Express that launched in 2005. And I was fortunate to be an interdisciplinary scientist on that mission. So it was a European Space Agency mission, but they let a few Americans on the team, and I was one of them. And it was a fascinating experience. It launched in 2005, and it orbited Venus until actually we lost contact in 2015. And it was really, Venus Express was a small but very well instrumented orbiter, and it was really our first weather satellite on Venus. It allowed us to make ongoing observations of the atmosphere and the infrared, and we saw things. We were able to see down through the clouds with infrared sensors, and so we saw these kinds of motions of the clouds that are these are the middle clouds, and these motions are hidden from our normal view, but we got sort of a more 3D picture of the way the atmosphere and the clouds were evolving and moving. Venus Express also detected what we think is evidence for active volcanism on the surface, because even though you can't really see the surface very well from orbit, it turns out that if you look at just around 1 micron in infrared wavelengths, you can get enough radiation leaking through the atmosphere and the clouds, that you can see some radiation coming from the surface. And by looking at the emissivity of rocks in different areas in these wavelength windows, we think we see evidence for recent volcanism on Venus. We'd like to confirm that with future missions, but as I mentioned, there's some circumstantial evidence for ongoing volcanism, and some of it comes from this Venus Express mission. Well, the Japanese also launched their first Venus mission, and that Akatsuki was launched in 2010, and it has a long wayward story where it made it to Venus but didn't make it into orbit. The main engine basically blew up, and Akatsuki went spinning helplessly around the sun. But amazingly, the Japanese are really good at rescuing missions that seem to have gone wrong. Amazingly, 5 years later, Akatsuki spun back by Venus, and they were able to put it into orbit, even though they didn't have a main engine anymore. They used the maneuvering thrusters, and they fired them all at once in the same direction and had just enough thrust. So they were able to get into orbit after all. 5 years later, after the mission was supposed to go, they got into orbit, and Akatsuki is still there today working. Several of the instruments have failed, but it's done really great work. And this is me with Akatsuki. I forgot about this. I got to visit the spacecraft at the Japanese Space Agency in JAXA outside of Tokyo before it launched. And over on the right, that's me in a bunny suit, standing next to the guts of the Akatsuki spacecraft. So this machinery that I'm standing next to here is actually in orbit around Venus right now, which is kind of fun. There's an artist's conception of the little Akatsuki spacecraft in orbit around Venus. And these are just some beautiful images. The cameras on Akatsuki, both the visible infrared and the ultraviolet cameras, are really sharp. And these are some of my favorite Venus images that just come from Akatsuki in orbit. And among other things, it got incredible images of the middle cloud region in the infrared. Just the detail in this is something else. And it discovered over here on the right some really neat features where this sort of giant ridge in the atmosphere. That's actually a big stationary wave feature in the atmosphere. And what's amazing about this is that it's over the tallest mountains in the equatorial region of Venus, an area called Aphrodite. And it seems as though this wave feature, even though it's 30 kilometers up in the atmosphere, or more like 40 kilometers up, is actually correlated with the surface feature. So there's some very interesting standing waves in which the surface topography so far below the clouds is actually influencing the structure of the clouds. We're still trying to understand that, but it seems as though it's correlated with the topography. So so Akatsuki has discovered some really neat things. Now, speaking of the clouds, I want to mention a sort of pet idea of mine that I've been pursuing for a long time that's recently gotten some renewed attention. And that is that the clouds themselves, even though the surface of Venus is obviously uninhabitable for life as we know it, because it's just so incredibly hot that, as I mentioned, any protein or any organic molecule would just fly apart in an instant. But if you go up in the clouds, you notice there's this range at about 60 kilometers where the pressure is the same as the pressure, or actually, I'm sorry, at about 50 kilometers, where the pressure is 1 bar, which is Earth surface pressure. And the surface temperature is also about 300 Kelvin, which is also similar to Earth surface temperature. So there's an area in the middle clouds of Venus where the conditions are not so extreme. And it turns out there are also some nutrients and interesting chemistry and some sort of unobserved some observations of phenomena that are not well understood, some anomalies in that region. So I'm not saying it's aliens, but no. So I've held out for decades, actually, the possibility that there could be sort of a habitable zone in the cloud region of Venus. Not that I think there's life there, but I think in the way that subsurface life on Mars is plausible, worth looking for, I think cloud level life on Venus is plausible, worth looking for. And recently, it's something I've kind of pushed as a little bit of a devil's advocate idea for a long time, and I've written some papers about it. But recently, it's been getting more attention. I think partly because astrobiologists are more comfortable with the idea of extremophiles, realizing that life can adapt to extreme environments. But also, we keep making more and more observations of this cloud region of Venus that don't quite make sense unless there's some unusual phenomenon going on. Now, unusual phenomena doesn't mean life, obviously, but I still, until we explore it better, I'm going to maintain that there's at least a plausibility argument there. So along those lines, there have been some interesting results about the history of Venus. I mentioned it early on. We think Venus probably early on was a more Earth-like planet and lost its oceans. But how long did it maintain those oceans? Was that loss of the water and that runaway greenhouse something that happened very early on? Or was it something that, did Venus maybe have oceans for a while? Well, we don't really know, but there've been some model results that have come in recently where we've finally been able to do real Earth-style general circulation models, GCMs, the kinds of models we use to predict climate change on Earth, where you put the whole atmosphere into a grid and you simulate the motions and the radiation and the precipitation and the clouds and all that, and you run it and try to simulate the climate of a planet. It's been a hard thing to do, adopting an Earth-style GCM to Venus, but it's recently been done, and we've got some really interesting results that led to this paper a couple of years ago. Was Venus the first habitable world of our solar system? By Mike Way et al. And you can see I'm one of the et al's here. I'm a co-author on this paper. But basically, what happens, and this was a surprising result, the reason why it's so hard to predict ancient climate on Venus, predicting the past is kind of a weird concept. We do a lot in planetary science. You might call it a retrodiction. But anyways, the reason it's so hard to simulate accurately the ancient climate of Venus is because it's very hard to get clouds right. Clouds are hard to model. And you need this kind of a GCM, general circulation model, to do the clouds in the right way. But one thing we didn't expect that we learned from doing this modeling is that if you simulate Earth-like climate evolution on a slow rotating planet like Venus, then the clouds do something really strange, which really has an unusual effect on the climate evolution. What happens is that the clouds organize themselves so that the sunward facing side of the planet is permanently cloudy, and the anti-sunward or night side of the planet is permanently clear. And that acts as a perfect shield to keep the planet cool, because the sunward side, the clouds are basically reflecting sunlight, and the fact that the night side is clear is allowing the radiation to escape into space. So if this model result is accurate, then Venus may have been cool enough to maintain oceans for billions of years, not just millions or hundreds of millions of years. So it may be that Venus, for most of its history, was an oceanic planet like Earth. And this is what our models lead us to, although obviously there's a lot of uncertainties and we need more data. But this is a startling result if it's true, because think of what was happening on Earth during all those billions of years, where you had the beginning of life, and then you had photosynthesis, and you had more complex life. If Venus really had oceans until just 1 or 2 billion years ago, then you basically had two habitable planets next door to each other through much of solar system history. And so Venus could have had an origin of life. It could have had complex life. It could have been exchanging life with Earth and maybe with Mars. We don't know. This is all still a model result, but it's increased our desire to go back to Venus and get better data so we can confirm or refute this idea. And I think it's part of what's led to a resurgence of this belief that there could be life in the clouds, because if Venus had a habitable environment for much of its history, as these model results seem to be suggesting, then it could have had a pretty robust biosphere that evolved. And then the question is, what happened to that biosphere when the oceans dried up? Did it just disappear? Or is it possible that some life migrated to a habitable zone that might exist in the clouds today? It's a speculative idea, but it's kind of fun to think about. I wouldn't personally, I wouldn't place money on there being life on Venus, but I do think it's worth, as we're investigating the planet for all the reasons we're interested, I think it's also worth doing some life finder missions, or including instruments on other missions that can investigate this idea. Well, now we're getting to the part of the talk where we talk about future missions, and I see I've used up most of my time, so I'm going to just quickly tell you about a few upcoming missions. This is very exciting to me because, along with some of my colleagues in the Venus community, I've been pushing and proposing missions to Venus literally for decades and getting rejected, and then NASA selects missions that go elsewhere, and we get almost there and we make it to the final round and we get rejected. Well, just as you may know, just in the last round of NASA mission selections, they selected 2 Venus missions, one of which, this mission, Da Vinci, I'm a co-investigator on. So this is something my colleagues and I have been working on and proposing for a long time. And we sort of got used to being rejected, to the point where when I got the phone call saying, guess what, they're going to announce that Da Vinci's been selected, I literally couldn't process that information. I was so steeled for another rejection that I wasn't prepared. and I had quite a, I think I started screaming and scared my poor dog. He thought maybe we were under attack or something. What I want to do now, I realize I'm pushing the time limit, but I want to show you a short, just a 2-minute movie, which describes some of what Da Vinci's going to do here. So I'm gonna stop sharing my screen just for a second so I can share this movie from a different program, and this should work. Let's see. Wait. Let's see. Okay, share screen, share sound. There, this is going to work. Oops, sorry. Oh, no, that's right.
Launching in 2029, the Da Vinci mission, named after Leonardo da Vinci, is designed to address fundamental questions about the origin, evolution, and composition of Venus. During 2 gravity-assist flybys, Da Vinci will study the cloud tops in ultraviolet light, tracking cloud patterns as they change with time and analyzing signatures of mysterious chemicals that absorb ultraviolet light. Both flybys will also examine heat emanating from the Venus surface on the planet's night side. We will look for geological clues of this planet's mysterious past to paint a global picture of surface composition and the evolution of the planet's ancient highlands. 7 months after our second flyby, Da Vinci will release its atmospheric descent probe. The spacecraft will watch its probe enter Venus's atmosphere over the course of 2 days. The probe will take about an hour to fall through the atmosphere, taking measurements and snapping images down to the surface. These measurements include profiles of composition, winds, temperature, pressure, and acceleration. Key gases will be measured to help us understand how Venus formed and evolved. Some of these measurements may reveal chemical signatures of ancient water. With our suite of measurements, Da Vinci will provide new insights into Venus's atmosphere's complex composition, structure, and chemistry. As the probe nears the surface, its descent camera will capture breathtaking bird's-eye views of the mysterious terrain known as the Alpha Regio Tessera, possibly revealing evidence in the rocks that water once flowed across the Venusian surface. These up-close images of the surface will provide new insights into geologic processes and will help us to understand what it might be like to stand on the Venus surface. An oxygen-sensing student collaboration experiment will shed light on the role of this gas in the Venus atmosphere. The discoveries that emerge from this diverse data set will tell us whether Venus was truly habitable. And the we reveal at Venus will reach even beyond the solar system to analog exoplanets that will be observed with the James Webb Space Telescope. Venus is waiting for us all, and Da Vinci is ready to take us there and ignite a new Venus Renaissance.
Okay, and then quickly back to my, to finish up my PowerPoint. Let's see if I can get this to work again. Is that working?
Looks good.
Excellent. Okay, so I want to finish up, but that was basically Da Vinci. By the way, that voice you heard was my colleague Jada Arney, who's the deputy project scientist of Da Vinci, and she did the narration, and obviously she's intricately involved in the execution of the mission. But I'm really excited about this fact that we're going to descend on this mountain range, Alpha Regio, and actually get descent photography for the first time. And as you may have gathered from that video, one of the striking things is that after all these years of prep and all this, we're launching in 2029 and the probe is going to get there in 2031. It's a 1 hour descent through the atmosphere that we're prepping for. Now we also have 2 flybys, so the mission is longer than that. But the actual descent from the top of the atmosphere to the surface, all of this data is going to be collected in 1 hour. So that's something that we're the ratio of time we're preparing to the actual duration of the mission is rather striking. Anyways, I want to wrap up because I want to make sure there's some time for a discussion, but I want to at least mention, because Da Vinci is not the only mission, it's the one that I'm heavily involved in, but there's another NASA mission called Veritas, which is also very exciting, which is basically a radar orbiter with much higher resolution than Magellan, and also has an infrared instrument that can look for some of these signs of active geology that we've been discussing. So the combination of our mission, Da Vinci, with this entry probe and this concentrated photography on one small area in detail, with the enhanced global picture we'll get from Veritas, the 2 missions are really complementary, and they're occurring in roughly the same time frame. I mean, Veritas is going to launch in 2028, and the mission's going to begin in 2030. Really, we'll basically be there at the same time. And finally, the European Space Agency has also just approved a new Venus mission called Envision, which is a somewhat different kind of radar orbiter, very complementary. In addition to very high resolution radar, it also has a subsurface radio sounder, so it's going to actually be able to detect subsurface structures, which we've done with great results on Mars. It's going to be the first time we've been able to do that on Venus. So we're really entering a new decade of Venus exploration with these upcoming missions, and it's been, for those of us in this community, have been hoping for new data. It's been a long time coming, and I guess when it rains, it pours sulfuric acid or something. But it's an exciting time to be in this field, because instead of just analyzing old data and doing models and complaining about not having new missions, now all of a sudden we have a lot to look forward to, and so it's really kind of invigorated our community, and it's something that we're all just really excited about. And with that, I'm gonna stop sharing my screen and go back to here I am, and I'd be happy to entertain any questions.
Starting off, if one were interested in astrobiology as a career, what would be the best post-secondary program or path to pursue?
Oh, great question. So astrobiology is inherently very multidisciplinary. So there are people that come into it from a lot of different angles. There are people who went to college and just studied chemistry or just studied biology or just astronomy or physics. You can come into it from a lot of different angles. So what I would say is, get a good solid grounding in some basic science, and then study broadly. Yeah, I mean, there's not one simple answer to that. It's and the other thing is, take advantage of the fact there are a lot of great resources for people interested in astrobiology out there. There's a group called, you can find them online, called SaganNet, like Carl Sagan, but I think there's two N's, SaganNet. And it's a group of young astrobiologists that mentor other astrobiologists and people that are interested in astrobiology. And there's a lot of really good opportunities for internships through NASA and other organizations. And so if anybody's interested, I encourage you to plug into the community of and on the online resources out there. And yeah, there's not just one path. You don't just have to go to college and study astrobiology. You can study any number of scientific fields and end up contributing to astrobiology.
Perfect. That's great. Thank you so much. We have a question. Is there an issue with solar radiation that affects the surface of Venus? And if so, has there or is there a magnetic field capable of resisting that radiation?
So yeah, Venus is interesting because it does not have an intrinsic magnetic field like Earth. And that was one of the things we discovered with the earliest missions. Was in fact that Mariner 2 that I mentioned was going to measure the magnetic field of Venus, and it got there and said, "Oh, there isn't one," which was kind of a surprise. It does have something called an induced magnetic field, which is a little bit like what happens to a comet, where the solar wind charges the upper atmosphere, and then because it becomes charged, it's the ions from the solar wind, it sort of generates its own magnetic field in response to the radiation that's coming from the sun. But it doesn't have the kind of protection from cosmic radiation and so forth that Earth does because of its magnetic field. But on the other hand, Venus has a very, very thick atmosphere that absorbs a lot of radiation. So if you were on the surface of Venus, in fact, you would not be bombarded by radiation the way you would, for example, on the surface of Mars with its very thin atmosphere, just because the atmosphere itself acts as somewhat of a shield. So, I mean, there's a lot of heat radiation at the surface of Venus because it's so hot, but there wouldn't be a lot of other sort of destructive cosmic radiation.
Cool. What combination of exoplanetary atmospheric gases would be considered a near definite indications of life?
Great question. So, near definite is an interesting choice of words, because I mean, there's a lot of debate about this. I mean, the first order thing you're looking for, you want to look for some combination of gases that's anomalous, that isn't obviously explained by geological processes. And then more specifically, you want to look for something that's out of equilibrium. Gases, atmospheres left by themselves, the energetically obvious chemical reactions will sort of happen, and what's left over is a sort of stagnant atmosphere. But something that's out of equilibrium, like let's say the sort of classic example we often come up with is if there's a lot of oxygen, but then there's also a lot of methane, because left to themselves, oxygen and methane react with each other and make, carbon dioxide and water. And then, so if you have an atmosphere with something really oxidized, like oxygen, and something really what we call reduced or hydrogen rich, like methane, they don't belong together. They would be reacting. They wouldn't be there unless there was an active source. So I would say that if you saw something like Earth, I mean, maybe this is geocentric, but if you saw an atmosphere like Earth and said, look at all that oxygen, that's unusual. Well, we know there are some non-biological processes that can create oxygen. But if you said, oh, but there's also a fair amount of methane in that atmosphere, if we saw that, I think that that would probably be considered a near definite sign of life. So yeah, I mean, it doesn't have to be oxygen and methane, but two gases that are obviously, don't belong together, that would react away and disappear unless something was actively sourcing them, is maybe not 100% indicative of life, but it makes you look at that planet and say, okay, what else can we observe about this planet that will either confirm or rule out the presence of life?
Awesome. We'll just keep moving on. We've got quite a lot of questions, but we'll just keep moving through them. Considering that the atmosphere of Venus is made of CO2 and the pressure is so high, shouldn't there be carbonate minerals forming on its surface as a consequence of basalt carbonation? Have any carbonates been detected by Venera or by any remote sensing method?
Yeah, great question. We have not seen carbonates on Venus. I mean, you have to consider the temperature too, and that not all phases of carbonates that would be stable on Earth, even in the presence of carbon dioxide, are going to be stable at those temperatures. But there's certainly some carbon-bearing minerals that you would expect. And we haven't detected them yet, but here's the thing. We have very, very little direct information about the mineralogy of the surface of Venus. Remember, there are those clouds, and all those Magellan images, we know the shapes of the rocks at some resolution, at some level of detail, but we don't have any spectral information about those rocks. And the spectral information we have is very scant because you're looking through that thick CO2 atmosphere. So one of the things we really want to do with future missions is get better spectral information. And in fact, Da Vinci, as it descends, is going to take some spectral information of that one Tessera area. And that will certainly be one of the questions we have, is what are the, if any, are the carbon-bearing minerals that we can observe on the surface.
Oh, that's awesome. Is there a cause and effect relationship between the speed of the atmospheric winds of Venus and its slow rotation?
Well, I mean, the basic, so as the questioner mentioned, and I don't think I even mentioned this in my talk, although I probably should have, is that one of the striking things that was discovered about Venus when we started dropping entry probes in, or even before that, when you just map the cloud motions, is what we call the super rotation, where the atmosphere is whipping around the planet very fast. We call it the 4-day super rotation. So that's more than 100 kilometers per hour wind speeds at the cloud tops, and it's in that same retrograde direction as Venus's rotation, but it's the Venus rotates very slowly retrograde, by which I mean if you were standing on Venus and you could see the sun would rise in the west and set in the east. It's backwards from Earth, but that's very, very slow. In fact, it's so slow that you can calculate, if you were standing on the surface of Venus, you could walk and keep pace with the sunset. If you were liking that sunset and you wanted to keep it going, you could just walk, and you could walk at the rotation rate of Venus at a human walking speed, and stay in the same place. So that's how slow the rotation of Venus is. But the winds whip around really fast in the same direction. And to be honest, we don't completely understand the relation between the two. The super rotation is something that we're still trying to understand with these GCM models I mentioned, these general circulation models, but it's obviously driven by solar energy, and it seems to have to do with wave propagation in the atmosphere. Some kind of solar driven waves is accelerating, is exciting those winds in the atmosphere, but they're not fully understood. And so the relationship with the surface rotation, therefore, is also not fully understood, but they are, they're both retrograde in the same direction. And clearly over time, there's been some exchange of momentum between the solid planet and the atmosphere, but we're not even sure if the slow rotation is a long-term feature of the planet. That was the one thing I didn't get into with the climate modeling. That whole conclusion I made about the slow rotation leading to the climate history because of the cloud distribution, that assumes that the slow rotation is an ancient feature. And in fact, we don't know the rotation history of Venus. And it may be that, as the questioner, I think, inferred, that the surface has exchanged momentum with the atmosphere. And in fact, that the atmosphere could have sped up or slowed down the surface as they've exchanged momentum. It's an area of it's still an area of great mystery.
Yeah, that's great. Given how metallic Venus seems to be, how is it that it doesn't have a magnetic field? And how is it that the CO2 atmosphere isn't stripped away by the solar wind?
So the lack of a magnetic field is a mystery. And, one thing that ultimately we're going to need to do, and, I didn't really have time to mention plans for far future missions beyond this next generation, but ultimately, eventually we want to have long-lived surface landers on Venus. And you would need some new technology for obvious reasons to do that because the temperature is so extreme, but there are some ideas about how to do that in the future. Just we have to develop those technologies. But one of the real driving reasons why you want to do that is so you can do seismology. We don't know anything about the interior of Venus beyond just extrapolating Earth models. And if you stop and think about it, how do we know anything about the interior of the Earth? We've never, despite some cheesy science fiction novels, we've never gone journeyed to the center of the Earth. But it's all by seismology. It's by listening, to the interior, by tracking seismic waves. So if we could do that on Venus, then we would understand, that the assumption is that it has a similar core to Earth's, but that assumption is just based on some crude assumption, crude inferences based on the bulk density of the planet. We know it has to have a metallic core the way Earth has a metallic core because its density isn't that different from Earth, but we don't really know how large that core is. We assume it probably has a molten core, again, because of the analogy with the thermal evolution of Earth, but it's, Earth's dynamo, Earth's magnetic field arises from the convecting and rotating liquid metallic core. And how analogous to that Venus's interior is something that we only infer really indirectly. And it is kind of a mystery. If Venus is so similar to Earth, why doesn't it have an intrinsic magnetic field? Some people have speculated that it has to do with a slow rotation, again, because Earth's dynamo is partly imparted by the rotation, but it seems to have more to do with the convection of Earth's interior, and Venus should have a similarly convecting core. So we're not sure why it doesn't have a magnetic field. That's a topic for future discovery. Now, as far as the atmosphere being stripped away, it turns out, and this is actually a result that came from the MAVEN mission on Mars. It turns out that the relationship between a magnetic field and atmospheric evolution isn't as straightforward as we once thought it was. And it may not be that magnetic field plays as key a role in protecting an atmosphere from being stripped away as we used to think it did. In fact, some of the scientists on MAVEN, which is the Mars mission that's there now, studying atmospheric evolution, think that, believe it or not, that it may be the opposite, that a magnetic field may help strip a planet's atmosphere away by sort of enlarging the magnetic cross section of the planet. So the relationship between a magnetic field and atmospheric evolution is, that's an evolving body of theory right now. But Venus is losing atmosphere all the time, as all planets are. Earth is losing hydrogen to space all the time. It's just a question of the rate. And if the atmosphere is being supplied at a rate greater than it's being lost, or if the rate of loss isn't significant enough to strip the planet away. And Venus, has so much atmosphere, and the source of that atmosphere seems to be a history of very active volcanism. And it may just be that that's more significant than the rate of any loss processes that come from the solar wind with or without a magnetic field.
That's really interesting. Why do we apparently not have meteorites ascribed to coming from being lofted off of Venus? Is it because of its atmosphere, or that we just can't recognize them?
Great question. I keep waiting for them to discover a Venus meteorite. I mean, after all, it was only in the I guess in the 1980s that we realized we had Mars meteorites on Earth, right? It's not like we've had them in our collections for hundreds of years and only realized that, you know, that some of the ones sitting on the shelves were Martian meteorites more recently. So could it be that we have Venus meteorites, but we haven't recognized them because we don't exactly, the reason why we know the Mars meteorites are Mars meteorites is partly because of the missions we've had to the surface of Mars. You know, Viking measured the rare gases on Mars to the point where we could recognize them in the gas bubbles in those Mars meteorites and go, aha, this matches. We never had a Viking on Venus, and we don't actually know the rare gases on Venus. In fact, that's one of the things we're going to do with Da Vinci. So it's possible that we have Venus meteorites, but haven't recognized them. But it's also possible that it's much harder to get meteorites off of Venus, possibly because of the atmosphere, as the questioner mentioned, but also just the gravity. I mean, part of the reason it's easy to loft meteorites off of Mars and get them to Earth is because Mars's escape gravity is so low, and it's just easier to get stuff off of Mars. It's harder to get stuff off of Venus. I mean, surely the largest impacts loft some stuff off of Venus, but the volume may be much less, and then there's a less of a probability of some of them ending up, you know, in Antarctica where they're going to be collected. So I'm still hoping, but we haven't found any yet.
Cool. What do you think of the idea that prokaryotic life might be fairly commonplace throughout the universe, but eukaryotic multicellular life might be extremely rare?
Well, it's an interesting idea. You know, I think that if you just extrapolate from the history of Earth, you know, there was a long period of time where there was just prokaryotic life. And everything else is much more recent. But I think you got to be careful because, you know, we tend to assume that Earth is sort of the normal planet and everything else should follow the same path. And it's you know, it's kind of the best we can do because we don't, you know, I envy the astrobiologists of the future who have, you know, 24 planets with life, and they can like actually infer the patterns and say what's weird and what's normal, if anything is normal. But we're not there, so we tend to overemphasize the history of Earth and assume that should be what's normal. If that is the case, then it may be that there's something hard about going to complex life, and that there are a lot of planets that sort of get stuck in or remain in for long periods of time in that phase of just single-celled life. But you know, so I think it's an interesting idea, but I just think that, you know, we also can't fall into the trap of like assuming that we really know the probability just based on the history of one planet.
Okay. Here's a fun question. Please share with us what exactly inspired you to start researching Venus, and what is your connection with the work?
Oh, it's an interesting question. I mean, okay, so when I was a kid, I was just fascinated in general with space exploration. I mean, it's kind of cliche, but I'm kind of a child of Apollo. One of my earliest memories in the fourth grade was staying up late and watching the astronauts walk on the moon, and blew my mind, like it blew everybody's mind. And then I was really fascinated as a teenager by that. You know, there was sort of when I was growing up, it was the first mission to Venus and the first mission to Mars, and the first the launch of the Voyagers to the outer solar system. You know, our first good looks at all these planets was kind of happening while I was at that age of trying to figure out what you wanted to do with your life. And so I was definitely drawn to planetary science as kind of this exciting adventure that I hope to become part of. Now, why Venus? To me, it almost seems accidental, but when I was an undergraduate, I got a summer research job working with a professor who was working with the Pioneer Venus mission data, and ended up sort of getting a summer job helping to analyze some of that data. And then when I went to grad school, it wasn't necessarily going to be Venus, but my advisor, a guy named John Lewis at the University of Arizona, when it was time to pick a research project, he said, well, here's half a dozen projects that that you could work on. And he'd started describing them. And there was one that had to do with the atmospheric evolution of Venus that just sort of really intrigued me. So it almost seems random now. It was kind of a couple of projects that I got latched onto when I was young, and then early in my education and early in my career. And then they were fruitful in that, that led to some results that actually I was able to publish a paper in a journal when I was in grad school about Venus. And then that was kind of cool and exciting. And that led me to, I don't know, it's kind of a one thing led to another, the fascination with Venus. I don't think it's inherently, the whole solar system is really interesting, but Venus just kind of became my thing. And then once it becomes your thing, then that sort of feeds on itself. I don't know if that's a very good answer, but
that's
that's
great.
The one I've got.
We've got a few more minutes for questions, and then we'll wrap up. I apologize, we're not going to get to everybody's questions today, but we'll try to answer a couple more. With the new missions, the assumption is that they're ready for the climate. Can you elaborate on that, and how long might they last?
I'm sorry, could you repeat that?
Sorry, with the new missions going to Venus, the assumption is that they're ready for the climate that they will experience. Can you elaborate on that, and how long might they last?
Yeah. So preparing a spacecraft for the environment that it's going to encounter is always a challenge. A lot of careful engineering and study and simulation goes into that. We have chambers at laboratories that try to simulate the radiation environment and the temperature. You do everything you can to test all the components in the environments or in simulations of the environments, and make sure that you're not missing anything that is going to fail because it's operating in an environment that it's not designed for. There's some famous examples from early in the space age where that wasn't done. People sending some of the early some kind of embarrassing in retrospect, some of the first attempt the Russians made to take photograph on Venus didn't work because the camera was fine, but the lens cap was made out of some stuff that melted on in place, and they never were able to remove the lens cap because it melted, which is terrible. But then, of course, they succeeded the next time. They did it. So, but so you don't want to have something like that happen. So you test, and you build in redundancy when you can. If something's critical, you try to avoid single point failures, things that can fail. If you can, you build in, a backup transmitter and backup as many crucial components as you can. So as far as how long they'll last, though, the Da Vinci mission I mentioned, it has a very finite life. It's an entry probe. And so it's only designed to make it to the surface. So it lasts, once it hits the top of the atmosphere, it's going to last for about an hour. And then it's possible it could survive on the surface for a little while and keep operating and send back more data, but it's not designed to have to do that. We've been lucky a few times. Like we sent a probe to Saturn's moon Titan called Huygens, which was the same thing. It was only designed to make it to the surface, but it lasted for about a half an hour on the surface and sent back some more great pictures. So we're open to that possibility here, but we're not promising anything that it's going to survive on the surface. So it's limited. Now with the orbiter missions, of course, they have a longer lifetime, and then you're talking years, and I think for Veritas, I think the nominal lifetime is a couple of years, but it's quite possible that things will keep working and then they'll get an extended mission. And once things are in orbit and are working, we have a pretty good track record of, look at some of the Mars missions where the orbiters that were sent up, more than a decade ago are still working. So in the orbital environment, you can have a lifetime of years or even decades.
Cool. cool. We'll maybe do one more. Why is the surface of Venus so youthful? Is it strictly due to volcanism, or is there something else going on there?
Yeah, that's a really great question. We think that a lot of it has to do with volcanism. And the reason I say that is, again, because if you look at that image, including the one that's right behind you there, Simon, I'm looking at now in your background, you see all those smooth areas appear to be basically flood basalts, as I mentioned. So a lot of the surface, a lot of that young surface appears to be volcanic. So we think that over time that's played a big role. However, that's clearly not all that's going on. There are also clearly areas where there's faulting and folding and various kinds of, Venus quakes going on. There's tectonic activity as well. So the planet seems to be, the landscapes are dominated by volcanism, but not only volcanism. There are other geological forces at work as well. And one of the big questions, and actually this is something that that Veritas is going to look at, is whether or not there's subduction going on Venus. On Earth, we have plate tectonics, where you have new plate being created at largely at mid-ocean ridges and seafloor spreading out, and then you have places where subduction, where old plates, parts of the surface, parts of the lithosphere, the outer rigid part of the planet, are being pulled into the interior, and the planet's kind of recycling itself. And we don't understand what the process is on Venus by which the surface might be recycling itself. But given that, as you mentioned, this surface seems fairly youthful compared to a lot of planets, there's got to be some kind of recycling process going on. So that's one of the things that Veritas is designed to try to ferret out.
No, that's fantastic. And I just wanted to finish off by asking, do you have any final comments before we close off this evening?
Oh, well, it's been fun to talk with you all, and thanks for all the great questions. And I just want to tell everyone to stay tuned, because a lot of this is sort of previews of coming attractions. And so, hopefully you can invite me back in another decade, and I'll tell you what we found with these missions.